What's up guys, welcome to my another paper review where we look at one of the most popular network in the field called EfficientNet. So the paper is named EfficientNet Rethinking Model Scaling for Convolutional Neural Networks. The whole paper is basically about how we can scale the network to balance the accuracy and computational resources we have. So they start with the abstract when they say that convolutional neural networks are commonly developed at fixed resource budget and they scaled up for better accuracy if more resources are available. So basically, if you think about it, it's you can use a ResNet as an example. So when you have, so you can use, if you don't have enough computational resources, you can use ResNet with 18 layers. But if you have much more, you can use the actually ResNet 152 or whatever resources you have. So it's been done before, but the process of scaling up ConvNets has never been well understood, and there are currently many ways to do it. So one way to do it is scale up the ConvNets by their depth. So that's what ResNet is doing, adding more layers on the top of it. Another method is width, so we increase the feature maps. And another less common but increasingly popular method is to scale up models by image resolution. Okay, so they actually got this nice visualization of it. So in the width scaling, we can basically just add more kernels, and what it does is we get more features, so we extract much more features. When we go deeper, we basically got much more stronger representation of the features we've got already, and the resolution is basically when we use higher resolution, more than 220 on 220, we just got more information on an image. So it's also increased the results we've got because we got more information. They actually tested for single, they only changed a single parameter. So here they change width, here they change depth, and the resolution. Basically, the accuracy gains quickly saturate after reaching 80%, demonstrating that limitation of single dimension scaling. So basically, it saturates when you only increase one of the parameters. And their first observation is that scaling up any dimension of network, width, depth, or resolution improves accuracy, but the accuracy gains diminish for bigger models. So obviously it just saturates, right? What if we combine all of them? So they also ran a test on it, and they fixed the width in this figure. They fixed the width, but they were changing the depth and resolution. So as you can see, the red one that performs the best has the depth 2.0 and resolution 1.3. So it means that combination of those features yields better result than just scaling single dimension. So that's the second observation, that in order to pursue better accuracy and efficiency, it is critical to balance all dimensions of network with depth and resolution during ConvNet scaling. Okay, so how we can basically scale it? You can do it like this. So basically you pick up the whatever parameter you want arbitrarily and see if it's performed well, but it's not a really good solution. The first thing is just you can scale 2 or 3 dimensions arbitrarily, but arbitrary scaling requires tedious manual tuning and yields suboptimal accuracy and efficiency. So it's not basically the best option to do. And they question, and basically the whole goal of this paper, the core idea, is there a principal method to scale up ConvNets that can achieve better accuracy and efficiency? And they propose one of this method called compound scaling. And yeah, let's see what it is in details. Compound scaling method, yeah. First of all, it uses compound coefficient phi, and it has 3 parameters. So basically alpha, beta, and gamma, and they depend on a compound coefficient, and they constrained by the equation that basically you multiply alpha, beta squared, and gamma squared. And that points out to 2 questions: what is compound coefficient phi and why they are squared in this equation. Phi is basically a user specified coefficient that controls how many more resources are available for model scaling. So basically we have the baseline network, and you can think of it as a ResNet. For example, the plain ResNet, maybe not plain, but basically ResNet 18, and it has certain amount of complexity that happens, so a certain amount of flops, right? And what you do by phi, you just basically change the complexity of the model. So if you increase it, for example, if phi is equal to 1, it has 2 times more flop than the baseline. And obviously if you increase it to 2, it has 4 times more complexity than the baseline model. We're gonna go through the network later on, but basically that's what the compound coefficient does. Why the beta and gamma is squared. So basically doubling network depth will double flops. So basically if we increase depth, it's gonna double the flops. but doubling network width or resolution will increase flops by 4 times. So that's why they are squared. And as you can see, they also why there's two. It's basically if we multiply alpha, beta, and gamma together, get them to the power of phi, they need to be equal to computational resources we've got. So I guess it makes all sense right now. It's basically going to be solidified more when we're going to write the code. But yeah, we can now move on to basically the network they use. So they have a baseline network, and we're going to go over the whole MBConv and what it is later on. So in total they have 8 models, and they call B0, B1, B2, and yeah, end up as a B7. And obviously the number at the end denotes the complexity of the model. So they started with the EfficientNet B0 when they applied compound scaling method. First of all, they fixed phi to 1 and do a small grid search for alpha, beta, and gamma. And they find the best values of them as alpha 1.2, beta 1.1, and gamma 1.15. And then in the step 2, they basically fix those values that they found in a grid search. They are basically training on the different phis. So basically the parameters that defines the computer resources we've got. So yeah, they did 8 models in total. And now we can move and we can see what the results of this are. So EfficientNet B0 has 5 times less parameters than the ResNet 50 and gets better results, which is crazy. And this is really effective, especially on the bigger models. So you can see EfficientNet B7 has pretty much the same results as GPipe, but it has 8 times less parameters, which is crazy. They actually did a graph comparison of all of these, and you can see basically how it performs really using so much less flops than the other models. And lastly, they also show how the compound scaling method helps to basically focus on more relevant regions with more object details. So they passed the maze, and they obviously they tested on the single values. It just performs better than the other methods. So yeah, so it's really interesting, and they also used a lot of different tricks to the implementation, and we're actually gonna go through them. So first of all, they use RMS prompt, which is not I haven't seen it in the previous papers. So the optimizer with the adaptive learning rate. And if you want to read more about the optimizer, you can check out my blog. It's going to be in the description. Yeah, they also use learning rate 0.256, which I also haven't seen before. But the most important, they use Silu instead of ReLU, which I'm going to explain exactly how it works later on. They also used auto-augment. So basically you learn which augmentation works the best. Okay, then we got the stochastic depth, which I also going to explain later on. And they use dropout, which I think I haven't seen for a while. Yeah, so that's all the tricks they used. Some of them are really interesting. And now I'm gonna go to the things that I skipped before. So we start with the MBConv block. MobileNet V2, they did kind of different blocks than we saw in ResNet or ResNext or CE block. So what they do, for example, if you have regular convolution, you just have, for example, 16 feature maps. Then you have 64 filters every filter goes through every of the 16 feature maps, then we sum it up and we got 64 filters in the output, right? Then we got separable convolution block. So what it means, it's a grouping convolution. So each feature has a one kernel from the output, and this kernel only looks at the one feature map. You just have one kernel for one feature maps in an input. And again, we got the 16 feature maps, and then we create the projection or to the whatever channels we want to have. Then we got bottleneck with expansion layer. So first of all, we start with 16 feature maps. Then we create the projections to 64. Then we do the grouping convolution, the same that we did here. So each feature map has its own kernel. And then we create the projection that basically reduce the number of channels again. So it's expansion and reduce again. So in this one, in MobileNet V3, first of all, we start with expansion. And then we got this depthwise convolution. So we group for each kernel. And then we got the squeeze and excitation. So what is squeeze and excitation? You can actually see my video. I did the review of the paper 1 week before, so you can check it out. And in a nutshell, it's basically for each channel in the input, we calculate the score, how important is the channel. So the importance of the channel can depend on what image you pass. So basically each channel is a feature. So for example, if you pass a plane to the network, you focus on different features than when you pass, for example, the image of the cat. So it's a kind of attention mechanism. And first it starts with squeezing. So global pooling is squeezing to 1-on-1. So basically one value for each channel. Then we got fully connected layers when we reduce the number of channels by certain ratio. And we got ReLU, another fully connected, which comes back to the same number of channels we've got. And sigmoid, because it scales down to values of 0 to 1. And later on, we just basically multiply it, so scale it by each channel. So we get weighted every channel. Yeah, if you want to know more about it, check out my video. And yeah, so that's basically it. And we just add this squeeze block at the top of the, so we just basically add this squeeze and excitation block. And when we again reduce the number of channels to whatever we had. So that's basically the whole block. We're gonna implement it in PyTorch. Then we got the silo activation function. The difference between ReLU and SALU is basically when you did the backpropagation through ReLU, you got this 0 value over here. So some of the neurons got never upgraded and it caused the dead neurons, and in some of the cases it can be 40% of the network, right? So in order to prevent these dead neurons, so they created this silo function which helps to prevent the dead neurons. Okay. So that's why they use it. And the last but not least, the stochastic depth. And it's pretty much the same as dropout. You can think about it as dropout, but what you do, you just basically drop some of the block in the network and it helps the generalization. Okay, so that's basically it. And with all that knowledge, we can actually go to Python and just code it. Okay, so first of all, I already written some of the code, or I copied it from previous project we did. Basically, I got the conv-block, which is slightly modified. So I add the act. In some of the cases, we don't need activation. Yeah, we'll see later on where exactly. And if act is true, we apply the silo. If it's false, we apply identity. And what is identity is basically just nothing. And I added the padding. So what it does is we divide by 2 kernel size. So in the case when we got kernel 1, we get the padding equal to 0. So that's what we want. Kernel 3, we got padding 2, padding 1. And when kernel is 5, we got padding 2. And it's extremely essential, especially when we change all the time the kernel size. And it's happening all the time in the EfficientNet, especially here. You see, we change the kernels all the time. So that's it. We got also squeeze and excitation block already written. We did it in the last week video. What we did, yeah. So we got global pooling, then we flatten it, we pass it to silo and fully connected layer, sigmoid and second fully connected layer. Then we change the shape to batch channels 1-on-1, multiply it, so basically scale it and return it. So it's pretty simple. I'm gonna write it again. And I prepare some of the comments and already written classes, because obviously there's no point of me writing again a super or init functions again. Okay, we start with MBConv Block. So basically what it takes is in channels, out channels, kernel size, stride, expansion. So expansion is in our network is this number. So basically when we got convolution 1, we got expansion 1, and when we got convolution 6, we got expansion 6. Okay, R is basically the parameter to SE block. I think in the first block over there, they use R parameter equal to 4. And another important thing, I haven't mentioned it, residual connections, we only apply it when input channels is equal to output channels. So we can start with defining first convolution, which is going to be ConvBlock, and it takes in channels, and we got expansion channels. So kernel size is 1, then the stride is 1. So what is expansion channels? Are equal to in channels time x. Okay, so what we got next? So obviously if we got the expansion equal to 1, we don't want to use this layer. It's pointless. It only happens if exp equal to 1, else identity. So now we got second layer, which is, so this is going to be expansion channels. Then we got kernel size find. We also use the pass stride, and groups is equal to expansion channels. Or this again because we do the deepwise convolution, right? So then we go the squeeze and excitation block, so it's SE block, and we pass the out channels or expansion channels. And then lastly we've got C3, which is ConvBlock with expansion channels, out channels. Kernel size is 1, stride is also 1, yeah, and act is false because we don't use activation at the last layer. So we also gonna define self add. So basically, as I said, we only add residual connections when the in channels are equal to out channels, and also when stride is equal to 1, because we can't add when we downsample it. Okay, so what we basically do here, we just pass the input. So I'm gonna call it F. So F is also and finally C3. Okay, then self add. So if self add, and then we do connection. Then we just basically add it and we return F. That's easy. That was pretty quick one. It's gonna get worse when we get to EfficientNet. But again, we got the classifier. Classifier is basically the last stage with average pooling and fully connected layer. So basically we got the conv 1-on-1 pooling NFC, and conv 1-on-1 can be still modified with channels and layers and resolution. Pooling NFC isn't. So basically we got the global pooling. So this adaptive average pooling, yeah, and the output size 1-1, and then we got FC fully connected. So this is linear, and this is in channels, and the output is classes, right? And we got dropout, and then dropout is we pass the P, so probability, and the probability depends on which version on EfficientNet we use. So forward is basically X is equal to dropout after pooling, and then we pass it to fully connected layer. Alright, that was easy, and that's the worst part of all of it. I left some comments to make it easier. First of all, we need to start with stages. So as you can see in the network, we got stages, we got operator, resolution, channels, and layers. So I wrote it in pretty much the same way. So we got the operator, channels, layers, kernel, stride, and expansion. So pretty much the same. And then we got phi's. So phi's is predefined, and for B0 basically phi is 0, then the resolution is 224, and dropout is 0.2. So that's the version basically of the EfficientNet, and they have their specific values. This is what we're gonna pass to our EfficientNet. And first of all, we're gonna get these parameters out. From phi's, we get the phi, resolution, and dropout value. Okay, so we got these three values. Then we defined network. So network is gonna be basically the list of all of these blocks that we predefine, that we create before. So we leave it first of all as an empty list, and then we create an empty list of channels, and we're gonna see why it's important later on. So at first stage we got the convolution 3-on-3. We extract those values first from stage 1. So it's gonna be operator, channel, layer, kernel, stride, and expansion. So this is stages 0. Okay, so we got all of these values. We create separate function called add layer. So basically we pass all of these arguments here. If layer is equal to 1, we basically just add one layer, right? So a selfnet append operator, and from operator we just pass in channels. Output channel is going to be C, so channels that we add, so the output channels we have in the stages. Then we pass the kernel, then we pass stride and the other arguments. So why we have args? So basically in ConvBlock, as we have here, we don't pass expansion, but in MBConv we pass expansion also. Okay, I hope it makes sense. So we basically just add one layer, right? But if we have more layers, we do it in a different way. So first of all, we add the first layer. So it's pretty much the same, but we don't pass the stride because stride is still 1. Then for all the layers between first and last, we append another layers. And then we get the final layer. We basically do the same, but the stride is equal to 2 or 1. It depends what we have in our stages. Lastly, we need to add channels. So that's the first one. For the next one, so that's 2 to 8 stages where we got MBConvs. We basically do the same, but we iterate. So for range from 1 to stages, should be fine. And then we basically do the same thing, but we obviously add channels, see? And oh yeah, we need to call add layer first. Alright, so it's gonna be okay, so what we pass is, so in the first one the input channel is gonna be 3. I know it's pretty complicated, it took me a while to understand it, so sorry for that, but yeah, so later on we add layer again, but yeah, so self channels -1, that should be better, and we add the expansion here. So basically the last one is pretty much the same. So last stage is with conv 1-on-1 and classifier, so this is -1, so last stage, and again we add layer, we channels -1 again, and we're gonna add layer with classifier. So we're gonna add classifier at the end, and classifier has in channels, which is self channels -1, classes, and P for dropout. Alright, forward is basically, it's pretty simple. So we iterate over, let's call it operation F in self-net, so the list with all our modules. And yeah, we just basically got X, F, or X, and we just return X. So this is pretty easy, but we only implement the baseline model. Now we need to look at the, yeah, so that's cool, we got the baseline model. How about the rest, right? How are we gonna modify it? So we need our coefficients. So I have 2 functions. So one is calculate coefficient, passed here phi, and as you recall in the paper, they just basically, how you calculate the depth is just you raise alpha to the power of phi and width, so beta to the power of phi again. So that's pretty easy. So we can define self d, which is equal to alpha raised to phi, and then width is beta raised to phi. Okay, so that's pretty straightforward. We're gonna add this at the beginning of the parameters here. So self calculate coefficient. Alright. We also need to update those features. So for example, if we iterate here and we got the layer, or even there, we got the layer, right? This layer is modified. So this layer is basically multiplied by the depth coefficient, and the same channels are multiplied by the width. Okay, so the same each time we call this stage, we need to multiply these ones to get the results. So for example, in B7 we have 3 of these layers, 6 of this one, right? So in order to do it, we got the update features, and we pass here C and L, so basically channels and layers, and what we return is integer C times self W, so width, and we return also L times self D, so basically depth. So we increase those values by width and depth. Okay, and where we're going to place it is the add layer function. So we do it at the beginning. It returns CNL, and we got the update features, and we pass basically CNL, and then we got the updated values of channels and layers. So yeah, that's pretty much it. I'm gonna just add one function. I'm gonna slightly modify forward just to print out all the stages. Okay, this is more fancier way to print it. We're gonna see in a sec. So that's pretty much it. We're gonna see if it works. I doubt it's gonna work first time, but let's see. Okay, we got some issues. Alright, there were 4 mistakes. They were pretty goofy, especially the first one. I haven't put the self-net append. I just put a layer. It should be self-net append. The next one was we also need to add the parameter for squeeze and excitation. So we set it to only for when the expansion is equal to 1. The other one, I haven't added the torch flatten over there in classifier. Here in the final layer, in add layer function, it should be C instead of in channels. I don't know what I put in channels. Anyway, it works well, and with the slightly modified forward function, it looks pretty nice. So yeah, we got the results pretty nicely. Let's check it for B2, for example. So yeah, as you can see, these values are changing. And to check, I actually did torch summary, and it gives you at the end the number of parameters, and it's almost 5.3 million. And as you can see here, it's, where is it? It's the same as they have. So, and the thing is, I haven't applied and I haven't put the stochastic depth, because it's another layer of complicated stuff on the top of it. It might be your homework. You can do it in your free time. I'm gonna add it on my GitHub with the stochastic depth, so you can then check it out how it looks like. And yeah, I think that's it for this video. If it was helpful and you enjoy it, just leave a like and hit the subscribe button if you want to see more of my content. And yeah, see you in the next one.